Okay, so we finished yesterday talking about derivatives. And derivatives really meant what for a graph? A derivative was the slope of a graph at any given point. And sometimes that meant things like instantaneous velocity, like you just had on your quiz. Now, that's really only half of calculus. The other half of calculus is doing integration. And what integration is the area under a curve, which, of course, in physics has some physical meanings. And you can check just by multiplying the units that you have on your axes. So if I had a velocity graph, velocity is in meters per second, time is on the x-axis, and I just multiplied those units. And that was partly why I had to do that in the summer work, dealing with units a little bit. Sometimes, if you kind of forgot a formula, you can check with playing around with the units. Do you get the right unit that you're expecting to get if you set up the formula this way? Anyway, this would give you meters, which would be a distance unit. So in this case, the area under the curve would represent the distance traveled at whatever time you've picked. So we learned how to do derivatives the other day. So now we're going to learn how to do some basic integration. And it's really the opposite steps you already took. And then we'll always have this plus a constant, because there may have been a constant there, we won't know, because what is the derivative of a constant? Zero. So how are you going to know if there was a constant there or not? That would have to be with some other information the problem gave you. But this is our notation for integration. You'll see this like squiggly line thing. And then you still have your dt. So this just means I'm integrating everything else with respect to time. Time is my variable. So when we did our derivatives, we would drop the exponent and subtract 1 from the exponent. We're just going to do the opposite for integration. So I'm going to still keep that constant there. There we go. Okay, so I've got my constant. Now, before I would drop the exponent and then subtract 1 from the exponent. So I'm going to kind of do the opposite. I'm going to add 1 to the exponent first. So now it's going to be 2 to the 4th. And instead of multiplying by that exponent this time, I'll divide by that same exponent I just made. Maybe. Okay, I'm going to have limited patience for this. We'll switch to markers here. And then if I have just a constant itself, what do you think that would be? What's the integration of 1 with respect to time? T. A slightly neater version, you'd have 2t to the 4th over 4. We can reduce that, of course, to being half t to the 4th. And then we have this minus 1. So we would need to throw in our variable there. And here's where you just have to stick a plus c, plus some constant. And you would need to just see your given information to know what that constant was there. Usually it's going to be 0 for us, but we'll see what the information says. Now, here's your double check. We just took the integration of this function. We've got this answer. If we take the derivative of this, we should get back to that. So you always have this double check. So this was my answer. Well, what is the derivative of all that? So I'll have my half. I'm going to drop my 4 down. Subtract 1 from my exponent. Minus 1. Derivative of constant is going to be 0. So of course that does give me back to what I had. All right. So integration basics. Take your exponent, add 1 to it, divide by that. If you have a constant, stick your variable on it, so minus 1t, and then always add that plus c. Okay. So here are a couple just to practice. Kind of do them together just to speed up my lost time. And like yesterday, if you have an exponent in the denominator, I like to make that a negative exponent. I think that makes a little more sense. Okay, so looking at number 1, t to the negative 3, what do we do first?
Add 1 to t to the negative.
We're adding 1 to negative 3, so t to the negative what?
Second.
Good. Yeah. Nope. 2. And plus c. So we could clean it up a little bit and put, negative 2t squared, maybe make it like that, plus c. Yeah, so square root of t would be the same as t to the 1/2. Okay, so what will we get there? We're going to add 1 to the exponent, but the exponent's a half. So 3/2, right?
Yeah.
And then over 3/2 plus our c, we can again, I don't know, maybe make it 2/3. Okay, and then same, if you are adding terms, you just do each term separately. So the integration of just t, add 1 to the exponent, divide by that. Integration of your constant plus 2t, just stick on the variable, and then plus c. All right, and then last but not least, 3t to the 5th divided by 5. All right, minus 5 t to the 3rd over 3 plus
No, t squared over 2.
Yeah. t squared over 2. Plus c. All right, that was a long one.
Will we have to do this out? I can't leave it like that.
I'm done with it. I'm not sure there's much else for us to do there. Yeah.
We'll just take them all to the same denominator.
No. All right, questions on that? I'm not even sure there is integration in your next homework. I think it's mainly graphing, but just so you know. So one more time, derivative meant slope on a graph, but if you're doing the integration, that means what of the graph? Area under the curve. All right, fill in this bottom part here. Okay, so in this chapter we're studying kinematics and position, velocity, acceleration, how they are all related to each other, how one graph can explain to you something about the other two. We learned yesterday, if you have a position graph and you want velocity, you do the slope. Same if you had a velocity graph and you wanted acceleration information, you would have to find the slope. But then the reverse is true. If you have an acceleration graph and you want to know something about velocity, you've got to take the area under the curve. Okay. This is the same graph from the other day. And in the other day we asked you what the acceleration was at point B. I'm doing the same thing here, except now I've given you the formula for the curve. The other day when we found the slope, we had this nice blue tangent line. You know, we just picked 2 points in the tangent line. We did a rise over run, we got -20. But if they are, telling us the exact equation, what do you do to get slope? Derivative. Okay, so this should be an easy derivative for us. What is the derivative of this function with respect to time?
17.
Yeah.
Negative.
Okay, so that's our derivative of the whole curve, any spot. And I specifically want to know the acceleration at point B, which lines up with 2 seconds. The answer would obviously be, yeah, just plug in your 2. There you go. All right, you kind of did that last night anyway. Okay, another graph. Okay, so we have another position versus time graph for a particle traveling along the x-axis. This is still straight line motion. Don't do the 9th grade mistake of thinking like something's on a roller coaster going like this. No, I mean it's just something moving, well in this case back, away, and then forward again. But straight line motion even though the graph looks like that. Alright, so part A, find the average velocity in the time interval from 1.5 seconds to 4 seconds. Again, this is kind of like your homework quiz. Average velocity, what pieces of information do I need? Yeah, and you might be able to fit this on this slide here. Yeah, the initial and final position. So velocity is displacement over time, displacement's final position minus initial. So what is the final position at 4 seconds? 2. So we're going to have 2 minus 8. And what technically is our time interval there? From 1.5 to 4.
2.5.
2.5. -6 divided by 2.5.
Negative 2.4.
And it's in meters and seconds. Okay. So that's your average. Part B, determine the instantaneous velocity at 2 seconds by measuring the slope of the tangent line. Okay, well they've drawn a nice tangent line for us, right at 2 seconds. Really pick any points you want so long as they're on that blue line. Hopefully we'll get the same things. I always like to pick, it's best, and we'll do some labs where you have to do some graphs and I'll ask you for like the line of best fit and what the slope of it is. It is best if you try to spread your points out as much as possible. Don't necessarily say, all right, I'm going to pick that point and that point right there. It could be a little more accurate if you came down, I don't know, here, there. All right, I'll go with that. And this is somewhat of an estimation. I'm assuming that this is where this line crosses. So I'm going down what?
Down 6
Over 3?
1, 2, 3.
Yeah, they're spaced by, I'm going from to, so yeah, 1.5. Uh, 4. Okay, so that instantaneous velocity obviously different than our average. And then at what value of time is the velocity 0, just by looking at it? No math here. Perfect. You know velocity would be 0 when the slope is 0. So just for an instant, I mean it's immediately changing before and after 4 seconds, but at 4 seconds the slope would be 0. All right. Now, a couple of homework problems will ask you to take one graph. It could be a velocity graph, it could be a position graph, it could be an acceleration graph, and draw the other two. So in this case, they're giving us a velocity graph, and it wants the corresponding position and acceleration. So, and I usually set them up kind of in order like this. You know, this is a position graph. I divide position by time, I get to velocity. Divide that by time again, I get to acceleration. And I like to mark off, not every single time, but the times of change where something different happens. So it looks like that would be at 3 seconds, 5 seconds, sort of 7. I'll mark it since it's a 0 point on this graph, and 9. Mark off 3, 5, 7, and 9. With a better scale than that. Same over here. Okay. So which one do you want to do first? Doesn't matter. All right, let's do position. And let's actually talk about like what this graph could represent. And instead of picking a car like I probably shouldn't have yesterday, I'm going to pick a little hovercraft. The little fan blades. Okay, so there you are on your hovercraft, powered by this fan, giant fan. Going to assume it's frictionless and air resistance is negligible, although if it's powered by the air, that's kind of weird to say that the air is negligible, but whatever. So if the velocity graph looks like this, what is happening to the hovercraft immediately? Speeding up. Speeding up, speeding up, speeding up. We get to about 3 seconds, and then what happens?
Stays the same speed.
Stays the same speed. Doesn't stop, but it stays at 8 meters per second. And then what happens? It's starting to slow down. So we've kicked the fan in reverse. And we didn't blow off ourselves, but we've kicked the fan in reverse, and we're slowing down. We do what for an instant right here? Stop. And then what? Reverse. Okay. So we're speeding up, same speed, slow down, stop, reverse. So that's what our other graphs also need to show. So if we're going to do position first, how do you get position from velocity? And you really only have two choices. It's either going to be slope or it's going to be the integration, which will be area under the curve. Now when I say area under the curve, it means from your graph to the x-axis, so to this line. And it can be negative. So divide it into shapes that you know how to find the area of. Yeah, I'm just going to consider this to be a triangle right here. So what is the area of this triangle? What is the area of a triangle? There we go.
So 1.5 times 8.
12. Okay. So I'm going to go to 3 seconds on my position graph, and I'm going to mark off 12. I'm just going to put a dot there. And we'll come back and think about how to connect these dots in a second. All right, keep going. The next section would be like this. What would the area of this middle section be? Yeah, this would be just sort of rectangle, so 16. Now, here's another thing to note. You don't just mark off 16 on your graph. At 5 seconds, you've gone how far total? 28. You've gone 16 meters, but in between 3 and 5 seconds. So total, you've gone 28 meters. So here's my best guess at 28. And try to do it to scale as best you can, because that will make your graph make more sense in the end. All right, and we got another triangle here. Back to 12. No, it's not 12. Because this is 2 seconds. Okay, and now this is how you would treat this little piece over here. So here's your area. So area from the graph to the x-axis, that would really be all this. So that would be but -8. It can be negative. Okay, so what was it all the way to 7 seconds? What's that total area? 36. Right? Plus 8, make it like there. Okay, so make a dot. Now, what about when you add in another -8? Back down to 28. Okay, so here's all my dots. These are the positions where I am at these given times. How do you make a graph out of this? Well, just think about it. Remember when we said we were speeding up, slowing down, or staying the same speed? The only spot where we were staying the same speed was between what and what time?
3 and 5.
3 and 5. So let's actually do that first. How would you connect these points? Just direct line, curvy. Yeah. So that to the best of my ability, the slope here is constant, and technically it should be 8. But I have a constant velocity, so that should be represented by a constant slope on my position graph. Now the other parts I'm either speeding up or slowing down. So from 0 to 3 seconds, I either want to have an increasing slope line curved like that, or a decreasing slope line. Yeah, you're speeding up, so your slope should be increasing. If speeding up means your velocity is going up and up and up, and velocity is slope, your slope should be going up and up and up and up. So just to the best of your ability, kind of curve that out into a continuous line there. You told me from 5 to 7 seconds we're slowing down. So the slope gets steeper or more shallow? More shallow. So we curve it kind of that way. And in fact, what exactly should the slope be at 7? 0. It should be flat right there, because we said we were stopped for that instant. All right, then moving on from 7 to 9. Which way? Should it get more steep or more shallow? Should actually get more steep, but more steeply negative. So it should be curved down like that. So my slope went from 0 to something negative, something steeper negative, even steeper. And of course, these are the values the slope should be becoming. So when you finish your graph, you can look at it. If you have like random jagged lines, like your graph went like this and then that is unlikely physically correct. So bear that in mind. You should have smooth transitions. Okay, so area under the curve was how we got position. Now acceleration. That's going to be what? The derivative, which is the...
Teachers, if you are teaching a 9th grade class right now and have not received their books, please escort them to the book room at this time. The teachers teaching 9th grade at this time, third period, please escort your students to the book room.
Okay, so we're now just going back to slope, which we are familiar with. So sadly, this isn't a whole number, but what is the slope of this line? 8 over 3? So 2 and 2/3? Yeah. Okay. Now, is that slope changing? Is this a curved line? No, it's not changing. This is a set slope, so it should be a set acceleration. So what should your acceleration graph look like? Straight, flat line. It is staying a slope of 2.67 for 3 seconds. How about from 3 to 5? What's the slope there? 0. So you just come down to 3 to 5 and make this your graph. And this is where it looks a little weird. And we are assuming that we have these set accelerations. Well, I mean, if this relates to my hovercraft, and I'm speeding up, my fan blades are running, I'm accelerating, and then I get to a spot where I'm just kind of cruising, maybe I've cut the fan. Well, there's still got to be some amount of time where the fan blades slow down and stop, right? It's physically impossible to go from this immediately to nothing. So we just kind of curve it out. Same here, it is physically impossible to have like a cusp like that. It would technically, if this were my real life example, have to have a little curve to these edges. All right, and then we could include 7, but really all of this is the same slope. Pick any points you want. But what is the slope of this line? Yeah, down 8 over 2, so -4. So I'm going to do the same thing. Sorry, all the way to 5, and kind of curve it out. But really, for the most part, and I think, even though I say this, you have one homework problem that's an exception, but for the most part, when they ask you to draw an acceleration graph, it'll probably be some step function looking graph. All right, so just once again, remember, if you want to go more simple, if you want to go to the left, you're doing area under the curve. If you want to get a little more complicated, from velocity to acceleration, you're doing slope. Questions on that?
For the last 7 and 9, it's still -4 acceleration?
Yeah, even that is the same slope. So that was where, like here, we had kicked the fan blade in reverse, so it slowed us down, stopped, and then sped us up going the other way. Okay. Another one. Okay, so number 6, a particle starts from rest and accelerates as shown to the right. The particle speed at, determine the particle speed at 10 seconds and at 20 seconds, and then also the distance. Okay, so this is an acceleration graph from which we would like to know something about speed. How do you go from an acceleration graph to get speed information? Integrate, which is the area under the curve. So the particle speed at 10 seconds, all right, well here's 10 seconds. I need all this area. So, yeah, 20. Now at 20 seconds. Now when it says at 20 seconds, everything that happened up until 20 seconds affects its speed at 20 seconds. So you have to consider all of the graph over to 20 seconds. So we said that this was 20. Well, what's the area between the graph and the x-axis if it's on the x-axis? Well, that part doesn't really count. That's 0 for us. This area is what? 3, 5. Okay, negative 15. So what's the answer? Is it negative 15? It's 5. So I am now going 5 meters per second. Which should sort of make sense because you've got now a negative acceleration. That's going to be slowing you down. So we've gone from 20 meters per second down to 5. The distance traveled in the first 20 seconds. Do we know how to get distance information from acceleration?
You gotta do, don't you have to do the derivative of the speed?
That would get me to acceleration, but it would be nice if I knew the speed. This is a big jump from acceleration back to distance. I know how to get from velocity back to distance like we just did. So you really need to do that. You need to make yourself a velocity graph, ideally quickly. And then we'll look at that to figure out the distance traveled in the first 20 seconds. And this is going to be velocity. So really over to 10 seconds, what was our velocity? Yeah, we just answered that. So that was 20. And we are accelerating. We have some acceleration. So what should the graph look like? Straight line? Well, flat, at least flat straight line or
Curved straight line.
curved?
Diagonal straight line?
Diagonal. I'm going to need some better descriptors. Just constant slope. And my slope should be 2, which it is. So let's see if I make that line up a little better. So my velocity is increasing, and this is where you have sort of some given information. My particle starts from rest. I did need to know that. All I know from this graph is that my velocity has increased by 20 meters per second. Well, maybe I went from 20 to 40. I don't know without this given information. So this kind of pertains to our plus c, that constant. That's given right there. So we're starting at rest, which we usually will be. So we've got the first part. Here we have no acceleration at all. So what is happening to the velocity? Straight line, staying at 20. And from 15 to 20, I end up at what speed? 5. So I got to mark that off. So that's my velocity graph. That kind of makes sense. Speeding up stays the same, slowing down. How do I use the velocity graph again to get back to distance? I got to integrate. I've got to do area under the curve. So just kind of use your geometry skills, break this down into shapes you kind of recognize. Even including here, even though this doesn't hit the x-axis, this area does count. All this area counts. So I'll do it, you double check me, see if we get the same total area here. I need, what? Yeah, what is 7.5 times 5? 37.5. And then, of course, find your grand total area. You agree? Any questions on that one? All get the same answer? All right, next. Okay, I think we only got two, maybe 3 slides left. All right, so we've definitely talked about acceleration already, but here is your definition. You know if something's accelerating, speeding up, slowing down. It is a vector, should have a direction. For this first chapter, we're just kind of indicating direction as a positive or negative value. But it's the rate of change of velocity. So your acceleration is change of velocity over time. If you want your instantaneous acceleration, you would have to do the derivative of velocity. And this is sort of how we came up with this notation. You'll see this in calculus. But remember, velocity was the derivative of position with respect to time. So if that's velocity, and acceleration is the derivative of that with respect to time, you end up with all of this notation. And that is a way of writing the second derivative of position. Okay, so describing motion with positive and negative signs. Talked about this briefly at the end of last class too. I think it's this slide and one more slide, then we'll be done. So what does it physically mean if you have, positive or negative signs for your velocity and acceleration? So all of these little scenarios pertain to my car here. This is my tree, the reference point at 0, positive directions to the right, negative directions to the left. And for every single example, I am pretending that the position is here. We're starting here for all of these. So I'm just going to put a little positive mark on every one of these graphs. So I'm always starting with a positive position. All right, then you just tell me, that's the car, it's going to be moving, and I tell you it has a positive velocity and a positive acceleration. What is happening to the car?
Speeding up.
Speeding up which way? Forward to the right. Exactly. So faster and faster, you just write faster and faster to the right. I wrote faster and faster away from the tree, given that it started there. What would your velocity graph look like? Yeah, just going up. And I told you it started as a positive velocity, so let's start our graph in the positive region. So just something like that, it's going up. But what about position? It's going up, but a little more specific. It's not a line. Yeah, the slope has to be getting steeper and steeper and steeper if my velocity is increasing. So, like that. So positive slope becoming steeper. That's a description of this slope. All right, what about negative and negative? Part of that's right. Definitely going to the left. But it's going faster and faster to the left. So that was one thing to note. If the signs match, that's always going to be faster and faster. So if it's negative, it's still speeding up. Another example would be like something falling down due to gravity. Velocity's down, acceleration's down, it speeds up. And I'll go ahead and fill these in as well. So these bottom two would be your slower and slower examples. And then we'll go back and make these graphs. You can maybe skip the middle line, like slower and slower, just which way, right or left. And I'm going to throw in the velocity graphs. Okay, so for the velocity graphs, again, just note how I drew those. In this case, we had negative, negative, so we had negative velocity, so I just start, below the x-axis there, start in the negative region. And the acceleration is negative, so my slope should be negative with a increasing but negative velocity. Here I start with a positive velocity but negative acceleration, and then vice versa, I start with a negative velocity but positive acceleration. But now I want to draw the position graphs. So if there ever is acceleration, your position graphs will be curved. It's just a matter of which way we're going to curve them, which I guess I've kind of given you the hints there. How about this? That graph right there. I've got negative velocity, negative acceleration. Yeah. Negative velocity, so it is negatively sloped curve, but it's becoming steeper and steeper, which it should be if I'm going faster and faster. If I'm going faster and faster, it should be getting steeper and steeper. If I'm going slower, it should be getting more and more shallow. So, perfect example, that one. Positive velocity to start. I'm slowing down. What's it going to look like? Yeah, it's becoming more shallow. I am still moving forward, just slower. And like we saw in that last graph, given enough time, which again doesn't really make sense for my car, but the hovercraft example maybe, given enough time, what might happen to this object? It's slowing down, slowing down, slowing down. Yeah, it may, if this acceleration continues to act, reverse directions and start speeding up in that direction. But I'll leave it as that part. All right, and then my negative velocity, but positive acceleration. So again, I'm slowing. What would that look like? Yeah, just mirror image of that. All right, one last slide, which is really just a summary of this. So these are your trends. Of course, if velocity and acceleration have the same sign, it's going faster and faster. If they're the opposite sign, it's going to slow down, and you guys just mentioned this. Given enough time, that object will stop reverse direction and speed up in that opposite direction. And if you remind me, we can do that one next time. It's just a matching signs problem. Checkpoint number 4. It says a wombat moves along an x-axis. And they do like to pick animals. You'll see quite a few penguins coming up. But what is the sign of its acceleration if it is moving in the positive direction with increasing speed? So remember we said if something is speeding up, what must be true about the signs for velocity and acceleration? They're the same. So for part A, what's the answer? So yeah, the same, so positive. All right, B, what if it's moving in the positive direction with decreasing speed? Good, negative. If it's moving in the positive direction, that's going to mean positive velocity. Slowing down, so we'd have to have a negative acceleration. All right, what if it's moving in the negative direction with increasing speed?
Negative.
Yeah, it has to match. Even if it's negative, it just has to match. So it's moving faster and faster, to the left, and then D, in the negative direction with decreasing speed.
Positive.
Good, so again, decreasing speed, the signs don't match, so that would have to be positive. All right, and I'll show you this little animation just real quick. Okay, so here's our car. It is set, I can't change this, it's set at an initial velocity, v0, meaning the velocity at time 0, at 12. And you can't see that great, but I can set the acceleration to something positive or something negative. If I set it to something positive, what will the velocity graph look like? Is it going to be curved or not?
No, just straight line up this way.
Good, it's a velocity graph. Now, if it was position, you're correct, it would be curved, and we'd have a steeper and steeper slope, but it should just be constant slope, increasing velocity. Okay, and I guess the car's gone. Negative acceleration, but it's still set at an initial velocity of 12. What would the graph look like? It would be slowing down. And, if given enough time, this was our if given enough time scenario, it would reverse direction. Now, one other point in the year, we'll do a web quest that has like a braking force. Realize that a braking force resists motion, so as soon as there isn't any motion, it's not going to apply anymore. So if this were due to the brakes, of course, it would just stop and be done. But I don't know, maybe it's just a really strong wind.
Where's video at?